Tasha, do you know what is one the Waals?
I think short-range electrostatic attractive force between uncharged molecules. So Haida, what is the main of characteristic of van der Waals?
Okay, the main characteristic of van der Waals forces is the first one, they are weaker than normal covalent and ionic bonds. And the second one, van der Waals forces are additive and cannot be separated. And the third one, there are no directional characteristic.
Wow.
Okay. That's all that I know from characteristic of van der Waals forces.
Turns out that all molecules contain this force. Oops. All molecules possess van der Waals. Okay, so I'm just going to put van der Waals. Okay? But they don't all possess it to the same extent. What that means is that some molecules are going to have higher van der Waals and some are going to have lower. Okay? So what makes van der Waals forces increase? The very first thing and most important thing is the size, and that has to do with the molecular weight of the molecule. The higher the molecular weight, the stronger the van der Waals. Pretty easy, right? Cool. Then we've got the second most important thing, or the second indicator, is going to be the shape. Okay? The shape of the molecule. And the shape has to do with how neatly they can be arranged and how neatly they can be ordered. So what I'm going to do here is I'm going to draw 3 different molecules, and you tell me which one would have the highest van der Waals force. So here I've got a ring, that's a 6-membered ring. Here I've got a 6-membered chain. And then here I've got another 6-membered chain. Okay? And what I want to know is, out of these 3, which of them is going to have the highest van der Waals? First of all, what we would look at is the size. Are all the sizes the same? Yes, they all have 6 carbons. So actually, in terms of size, they're fine. Okay? Then I would look at, okay, the shape. Which one has the shape that can arrange the neatest and can stack the best? And the answer is the ring. Because check it out. The ring, actually, since it's so symmetrical, it can have a bunch of rings stacked on top of each other. So if I wanted, I could keep drawing these rings stacked on top of each other. You know what that means? That there's intermolecular van der Waals forces all in between that, keeping them stuck together. Does that make sense so far? Then with the chains are still pretty good, but they're not quite as good as the rings. So here I'm drawing an example of van der Waals forces here. These are okay, but they're not quite as good as the rings. Does that make sense? And then finally we've got the branch, which I'll try to move out of the way, because I know that it's right on top of me. But with the branch, what we find is that there's not really a great way for them to stack together. They wind up kind of having a lot of space in between them. Does that make sense? So the van der Waals forces here are going to be very small compared to the van der Waals forces here for the rings. Does that make sense? Cool. So basically, I hope that this clarifies intermolecular forces. The first thing we look for is the type of force. Hydrogen bonding is the best. Van der Waals is the worst. Dipole is in the middle. And then we kind of break it down from there. Okay? So now what I want to do is do a few practice problems so you guys get comfortable with this. And I'm going to try to trick you a little bit. So be prepared, alright? Let's go.
Basically, van der Waals is about forces that involve attractive and repulsive electrical force that involve between atoms and molecules.
So there are 3 types of van der Waals forces. First is London dispersion forces, second dipole-dipole forces, and third is hydrogen bond.
It's midnight, and all is still, except for the soft skittering of a gecko hunting a spider. Geckos seem to defy gravity scaling vertical surfaces and walking upside down without claws, adhesive goos, or superpowered spiderwebs. Instead, they take advantage of a simple principle, that positive and negative charges attract. That attraction binds together compounds like table salt, which is made of positively charged sodium ions stuck to negatively charged chloride ions. But a gecko's feet aren't charged, and neither are the surfaces they're walking on. So, what makes them stick? The answer lies in a clever combination of intermolecular forces and structural engineering. All the elements in the periodic table have a different affinity for electrons. Elements like oxygen and fluorine really want electrons, while elements like hydrogen and lithium don't attract them as strongly. In atom's relative greed for electrons, it's called its electronegativity. Electrons are moving around all the time and can easily relocate to wherever they're wanted most. So when there are atoms with different electronegativities in the same molecule, the molecule's cloud of electrons gets pulled towards the more electronegative atom. That creates a thin spot in the electron cloud where positive charge from the atomic nuclei shines through, as well as a negatively charged lump of electrons somewhere else. So the molecule itself isn't charged, but it does have positively and negatively charged patches. These patchy charges can attract neighboring molecules to each other. They'll line up so that the positive spots on one are next to the negative spots on the other. There doesn't even have to be a strongly electronegative atom to create these attractive forces. Electrons are always on the move, and sometimes they pile up temporarily in one spot. That flicker of charge is enough to attract molecules to each other. Such interactions between uncharged molecules are called van der Waals forces. They're not as strong as the interactions between charged particles, but if you have enough of them, they can really add up. That's the gecko's secret. Gecko toes are padded with flexible ridges. Those ridges are covered in tiny hair-like structures, much thinner than human hair, called setae. And each of the setae is covered in even tinier bristles called spatulae. Their tiny spatula-like shape is perfect for what the gecko needs them to do, stick and release on command. When the gecko unfurls its flexible toes onto the ceiling, the spatulae hit at the perfect angle for the van der Waals force to engage. The spatulae flatten, creating lots of surface area for their positively and negatively charged patches to find complementary patches on the ceiling. Each spatula only contributes a minuscule amount of that van der Waals stickiness. But a gecko has about 2 billion of them, creating enough combined force to support its weight. In fact, the whole gecko could dangle from a single one of its toes. That super stickiness can be broken, though, by changing the angle just a little bit. So, the gecko can peel its foot back off, scurrying towards a meal or away from a predator. This strategy, using a forest of specially shaped bristles to maximize the van der Waals forces between ordinary molecules, has inspired man-made materials designed to imitate the gecko's amazing adhesive ability. Artificial versions aren't as strong as gecko toes quite yet, but they're good enough to allow a full-grown man to climb 25 feet up a glass wall. In fact, our gecko's prey is also using van der Waals forces to stick to the ceiling. So the gecko peels up its toes and the chase is back on.
Graphite is composed of stacked layers of graphene sheets which are held together by the weak van der Waals forces. Geckos also can stick on the wall because of van der Waals force.
Second is gecko. The gecko have tiny hair on their feet, approximately 20 nanometer in diameter, and then this tiny hair branch out to create a very large surface area and create an attractive force with a wall that is strong enough to counter gravity. And then this is where the concept of the dry adhesive comes from, the mimic nature and have a surface that will stick without leaving any sticky residue when removed.
Hi, my name is Aiman Hakim, and what I can summarize from all of my friends talking about is van der Waals force are relatively weak electric force that attract neutral molecules to one another in gases, liquid, and solid, and it's almost in all organic liquids, solid, and also okay. Why is called a van der Waals? It's based on a Dutch physicist John Diederik van der Waals, who in 1873 first postulated these intermolecular forces. Okay. What I can say about the van der Waals forces is have a lower melting point. Van der Waals a weak force between contribute to intermolecular bonding between molecules. The molecules inherently possesses energy and their electrons are always in motion, so transit constellations of electrons in one region or another lead electrically positive regions of a molecule to be attracted to the electrons of another molecule. And lastly, nuclearly charged regions repulsed by nuclearly charged region of another molecule. Right? There are three types of van der Waals forces. First, diffusion, which is weak. Second is a dipole and dipole, a medium force. And also the very strong one is called hydrogen. Diffusion, also known as London force, is an attractive force that arises between temporary dipoles and induce dipole in atoms or molecules. The larger the molecule, the stronger the dispersion of force. Next, dipole and dipole force is a force of attraction between polar molecules. For example, one molecule of H2O, water, is attracted to another H2O molecule because H2O is a polar molecule. Lastly, the hydrogen bond, a really strong van der Waals force, is a special type of dipole-dipole interaction between the hydrogen atom in a polar bond like oxygen and hydrogen, or nitrogen and hydrogen, and the electronegative atoms such as nitrogen, oxygen, and phosphorus. These are the much stronger force of attraction than other dipole and dipole force. Okay, by all that,